Hello, and welcome to Lesson 10.4 on applications of exponential and logarithmic functions. Actually, if you notice the title at the top of this note packet is incorrect. It is not properties of logarithms. That's not what we're talking about in this video. It's what I just said, applications of exponential and logarithmic functions. So what we're going to do in this video is explore the many different uses of exponential equations and how we can use logarithms to solve those. Yeah. We're not actually taking a look at a whole lot of logarithmic functions. Those have their place. I think that's a discussion a little bit more geared towards pre-calculus. That's where you might use more logarithmic functions to model some real-world scenarios. What we're going to be doing is looking at exponential functions and using logarithms to either create the functions, evaluate the functions, or answer some pieces of that kind of stuff. So that's our goal. So a quick little preface, a little before we get started with everything. In this lesson, we're going to talk about the various formulas used for these different applications. And I'm going to say it's important to understand that each of these functions tell us the same story. Thing is, we start out with an initial amount. We start out with some beginning value, and then with that value, it's either going to grow or decay exponentially. So it's either going to grow really fast or it's going to decay really fast. When I say decay, kind of means like decrease. It's a decreasing function. Yeah. So I ask you to examine the table below for some common exponential formulas. So you're going to see these formulas in a variety of contexts across different disciplines, okay? When you start really focusing in on a particular discipline, when I say discipline, I mean like a subject, right? Like you focus in on biology. You are a biologist. You are working with biology things. You're not concerned with, say, another discipline like statistics or finance, right, or economics. Which you could still use exponentials for, but you're working and operating within your own context. So I'm going to look at these formulas and kind of give you the rundown. You've got your basic exponential function, which is y equals a times b dx. This is the one you're introduced to in Algebra 1. It's just the basic definition of what an exponential function looks like. The rest of these all follow that same format. They just they're used for different applications, and we choose particular letters accordingly. I am going to go to the next page and actually explain this more in depth, but you can see exponential growth and decay. You see compound interest, continuously compounded interest, half-life, and the law of exponential change. And you might notice that continuously compounded interest and the law of exponential change look pretty much they pretty much are the exact same thing. Well, guess what? All of these are pretty much the exact same thing. They're written a little bit differently, and maybe they tell you different information, but they could all be used to solve or model pretty much the same problems. Okay? We're going to explore the relationship between all these formulas back and forth. And lastly, before I go to the next page, you don't need to memorize these, okay? That is okay. You will be given these formulas, and all you're really looking for is when you read a word problem, maybe look for the word compound interest. If you see the word compound interest, you know you probably need to use a compound interest formula, yeah? Okay, so let's go to the next page. And so this is just going to be some note-taking. This lesson video is just everything we did in class. So if you were absent or just need a recap, here's what we covered in class. Now I'm going to kind of shoot through this with minimal explanation. If you've already got this section filled in or you want to look at the notes online, just skip this part, okay? I'm just going to be talking. That's it. Okay, so exponential growth and decay, that formula. We typically use this for problems concerned with annual growth. Now, notice the word typically. It's typically. It's not always, okay? You can use this for any time frame you want. You can say monthly growth. You can say daily growth. That is fine. But a lot of times, I would say the most common thing, at least that I've noticed, is annual growth. At least what we deal with in Algebra 2, that extent, okay? The equation often uses P. Now see, here's the thing. We can use any letters we like. We can use any letters. It does not matter. And when you're looking at these, I'm going to go back to the next page. Look at all this. You got P, you got R, you got, all of these have P, R. You got N, you got A naught, you got HL, right? You got C, you got K, right? You have all these different letters. These letters usually come from the context you're operating in, okay? But they often kind of mean the same thing. So we use P to represent the principal amount. Now, in finance, notice it says finance. In finance, a principal investment or a principal amount is how much is originally invested. It's how much you originally start with. It's your beginning amount. That's what principal means. It's important to note that R is our annual growth rate. Okay? So it doesn't have to be. It could be daily, right? You could say monthly. You could say daily. And this would be acceptable. But more often than not, it's usually annual. Okay? And so we would say that this is a percentage increase or decrease per year. And if it's not per year, it could be per month, it could be per day. But the idea is you're looking at the growth with regarding to a particular time frame. Okay? And that's going to differ as we go on. Now, compounded interest. Notice interest does not always increase just annually. It can increase monthly or daily, and that's said above. But compounded interest it's a little bit different. Okay, so we say N, this letter N, you're going to see it in the formula, is the number of times interest is compounded per year. So let's say, for example, if interest is compounded monthly, then that would mean, well, there's 12 months in a year, right? Since it's, let's say I have like an annual interest that's compounded monthly, and there's 12 months in a year, then that interest is compounded 12 times per year, therefore N equals 12. And we would use that in part of our equation. So pay attention to that, right? If it's annually compounded, but like every month, then you would look, 12 months in a year, okay? You got to pay attention to that context. Now, what does this mean exactly? Well, think of it like this. Let's say I invest $100, right? And let's say it's compounded with a 5% interest. And let's say this is compounded, like we said, monthly, right? Then after the first month, I'm going to multiply this by 5%, add it to 100. So that would be $105. Now the thing is, now that this amount has increased, the next month, you're going to get that 5% on the new amount, on the 105. So you're going to take 105 and multiply that by 5% of that. I actually don't know what that is. Do I have a calculator real quick that could... Oh, don't make the runtime too long, Mr. Spake. Hello, I just want to do a quick calculation to show my students. Let's say 100 times 1.05, right? I get the 105. Now I multiply by it again. I get 110 and 25 cents, okay? So say 110.25, right? And so it's compounding monthly means you start to begin earning interest on your interest, right? That is what's happening. This is a tad different from just the general exponential growth formula. And we can talk about the distinctions when we get to a particular problem, okay? But I would sum this up as compounded interest means not only does your original investment get interest, but your interest gets interest, okay? Now, continuously compounded interest means that an interest rate is compounded instantaneously. instantaneously. And when I say instantaneously, I mean instantly, right? You have to think, it's kind of hard to conceptualize this. It's not a particular time value, but you can kind of conceptualize it as a particular time. So continuously, instantaneously means every single second. And not just every second, but every half second, every millisecond, every nanosecond, right? We are talking about the instant rate of change. Is interest rate. Well, I shouldn't say, not the rate's not changing, but the value is changing every instant according to this rate. And the thing is, the number E, which remember the number E is about 2.718, has its origins from the compound interest formula. And this is when you take in, which is how many times you're compounding it, and you make that go to infinity. So you increase that in value, how many times it's compounding, to infinity. That's where E actually kind of comes from, or at least it's one of its origins. Okay. Again, more on this later. It becomes much clearer once we start talking about problems. Next up is half-life. Now, half-life is an exponential decay function, and I'll explain this. You say A naught, that A sub 0, is the initial amount, much like P. So remember, up above here, we said that P was the principal amount, and principal means originally invested. Well, when you're talking about half-life, we don't use half-life equations for finance. Really? At least I don't think I've ever seen that, because it's usually biological or physical or something of that capacity. So this is more of a biology thing or a chemistry thing with half-life. So we use A naught because the little sub-zero means initial. Usually it's like a math thing, right? A sub-zero means the beginning amount, and A being amount. So it basically is the same thing as P. We just use a different letter because it's a different context. Now, HL, as you could probably guess, stands for half-life. So HL is how long it takes for the substance to decay to half its original amount. And I want to say it's important to note that half-life is a measurement of time. Okay, so a half-life of an element or a substance or a compound, it's not a rate, it's a time, right? You might say that the compound of this element is 12 years. That means if you start with some substance, some amount, it will take 12 years for that substance to decay to half of what it started at. That is what it has. So it's a unit, it's a measurement of time. So be careful with that. The last is the law of exponential change. And this is just a general continuously compounded interest function using constants C and K. We use this just in other contexts aside from economics and finance. All right. Economics and finance, you say A equals PERT, P times E to the RT. Well, we're not always talking about principal, and we're not always talking about this particular rate with regard to interest rates, right? So we generalize it as A equals CE to the KT. But guys, P and C are the same thing. R and K are the same thing. It's just different letters, all right? C is still the initial value. That has not changed. And K is the continuous growth rate, okay? There's absolutely no difference there. You might say, well, then why would we bother with this? This one, at least in my experience, I've seen this used more for calculus, and particularly a certain math class called differential equations, which is something you take after calculus in college. Often these are our generalized exponential change functions just in mathematics. So think of that as more of a pure math approach, where maybe it's more absent of context, okay? But you can still use it for all this stuff. Now, last thing before we get to the math problems and things like that, is a quick reminder. I say, we talked about this in the last unit, but we got to talk about it one more time because I don't think all of us are getting it, and that's okay. We're just revisiting it. When you're asked to write a general equation, this means you're writing an equation that generally models the relationship in the problem. So for example, let's say I have this exponential function for exponential change, y equals c times e to the kt. This is a general equation that models exponentiation, but look, we don't know what the heck c or k are, right? We don't know what those values are. It's a general equation that models the type of change or relationship that's occurring, but we don't have any real context about it, okay? Or what's more than that is finding the particular equation. Now you see, the particular equation means you have that context. It means you have a particular relationship between certain variables, and you're operating within a context of a problem, right? So really, it's like the general equation, but you found what c and k are because you found the actual initial amount in reference to this problem we're working on. I hope that I make that clear because we asked that you guys write particular equations on the last test, and I don't think we quite got it. You gotta take what you solved for and put it back into the equation, because what you're doing is writing the function that particularly models this scenario. Okay, I hope I've made that clear, but let me know if you still have any questions on that, okay? All right, here we go. I'm so excited. This video is probably gonna be long, but that's okay because I love this stuff. All right. This problem, number one here, Mr. Spake made himself completely. I did not pull this from a textbook. I didn't do any. I made this up myself because I wanted to, and I like it. So here we go. Suppose that after financial aid and scholarships, you've taken out $32,000 in student loans. Not an uncommon thing in the United States of America. The federal interest rate for undergraduate students currently, as far as I can recall, is 3.73%. And that doesn't change. It's a fixed interest rate. Now, most people, I've looked this up at least, most people aim to pay off their student loans within 10 to 20 years. So you take out your loan, you go through college, you do your 4 years of service, and then over the next 10 to 20 years, you aim to pay it back. Now, so who knows? You might be paying them 30, 40 years, right? No one says whatever, but that's most people, 10 to 20 years. Okay, so here's what we're going to do. We're going to assume that the interest rate is compounded yearly. We're going to analyze this problem from a multitude of contexts, right? Or I should say using various models. So we're going to do interest rate compounded yearly. So what does that mean? Well, it means, so you say compounded yearly, right? Now, look, it says compound interest, but really what this is, you might see the word compound and think, okay, I got to do this, but it's yearly and time is in years. So N is 1, okay? It's being compounded yearly where time is in years. So N is 1. So if you make this 1 and you make this 1, it's just the exponential growth function. That's generalized right there, okay? So we're going to write the generalized exponential function for exponential growth. We're going to start with the general. So here is the general equation. It's A equals P times 1 plus R to the T. And here's some reminders. A is your final amount. P is your principal or initial amount. R is the interest rate per year. And time is time in years. Okay? What we got to do is find the particular equation, which means we need to figure out what all of these letters are. Well, it says that, and my function is A. So you want to say that A equals, because what we're doing is we're writing a function that tells you the final amount after some time. That says that the initial investment, or I shouldn't say invest, it's not an investment, it's a loan. The principal loan, right, is $32,000. That's what I'm starting with. And then I'm doing 1 plus the interest rate is 3.73%. Now, what that tells you, so see, you're going to say P equals 32,000. And you're going to say R equals, that's a percentage which you want to do as a decimal, 0.0373. Now, if I add that, right, it's 1 plus 0.373, well, that's just 1 point that, right? So it's 1.0373 raised to the power of t. Done. That's it. That's all it asked, okay? You have created the particular equation. Do you see how this is different from the general? We have the general growth function, but we've given it context with an initial value and an interest rate. You might say, why don't we have something plugged in for t? T is a variable. T is time. The function depends on t, okay? We don't need to plug anything in there. Okay. Now, let's calculate the total money you would owe if you did not pay any of the debt off for 10 years. Now, look, this is hopefully unlikely. You don't want to wait 10 years to actually start making your student loan payments, but suppose you did, okay? So I'm going to say this. A is a function, so I'm going to write A of 10 versus A of 20. Now, what A of 10 means is 32,000 times 1.0373 to the power of 10. And A of 20 means 32,000 times 1.0373 to the power of 20. Now, I'm going to go to a calculator real quick and plug these in. Where is my graph? There's my graphing calculator. Cool. And so, look, if you want to skip through this calculation, do that, okay? I'm taking it slow in this video. I'm just being leisurely. 32,000 times 1.0373 to the 10. Calculate. So I get about $46,152. Okay? Look, you can put the 34 cents there. Who cares? Okay? It's fine. I'm going to just round to the nearest whole dollar. Let me enter this again, but then change this to 20, and I get 66,563, or maybe 64, rounding up. Okay? So I'll write those down. So after 10 years have passed, my loan has increased to $46,152. If I don't pay anything for 20 years, that's going to be $66,564. Now, I want you to notice kind of the difference here, just looking at the numbers. The first 10 years, 32 increased to 46. So that's about a $14,000 difference, right? That's roughly $14K over those 10 years. But on the next 10 years, between 10 and 20 years, that's roughly $20K. Yeah, so this first 10 is $14K in interest, but the next 10, it's $20K extra in interest. So it's growing exponentially. All right, part B. Let's say even though student loans are expressed as an annual rate, the interest is actually compounded daily. This means, so when we say an annual interest rate, here's kind of what it means is every year, that percentage is then going to get applied to the amount you owe, right? And that's what it means for an annual interest rate. That percentage gets applied every year. Once January 1st hits, boom, percentage increase. Your loan is bigger now. However, if it's compounded daily, that means every day it's increasing. It's that percentage rate is applying to your loan every day. And so this is, since you see this context compounded daily, you know that there's 365 days in a year. So let's write the particular equation. We're going to use compound interest. This is A equals P times 1 plus R over N to the NT. Now, you don't have to memorize that. All you got to do is look at that list, notice it's compounded daily, and figure out what we need to use here. So let's make the particular equation that represents this. Well, A is still that final amount. P is still $32,000. That has not changed. But now it's 1 plus R, which is 0.0373, divided by N. And you see N, if we go back here, where does it say? N is the number of times interest is compounded per year. So it's compounded every day per year, right? So there's 365 days in a year. And I'm raising this to the 365 because that's N times T. That's your function. And now I might say, okay, well, how could I express, like, can I make this a nice, pretty one solid value? Let's go type that into a calculator just to see, 0.0373, and let's divide that by 365. That's a really small decimal. I mean, that's incredibly small. And we want super accurate. You know how I've told you before, don't round too early, not when you're creating your functions. Don't round too early, because if you round too early, who knows how accurate your estimations are going to be. So what I'm going to do is just leave the answer like that. That's it, okay? That is the exact model. I'm not going to calculate this and then round. Does that make sense? Don't calculate that and round. Your model then becomes less accurate. Just use that expression. I know it's a little ugly, but it's fine. Okay, part 2. Let's calculate the total money if you... Oh, okay, so same thing, right? A of 10 and A of 20. Same story, no different. And you're just going to use this. So we'll come over here, right? We'll say 32,000 times 1 plus 0.373 divided by 365. So the power of 365 times 10. Boom. 46,400. Boom. Good stuff. And so I'm going to just write down my answers here because I've already done these calculations and you don't need to see me type them both. So here's the first calculation, and then if you do it for 20 years, it's about 67,471. Now I want you to compare these amounts, right? The models are pretty similar, right? Don't you see, right? 46,400, 46,100. That is pretty similar. This one's a little bit different. It's about $1,000 difference, which is, depending on who you are, that could be significant. Depends on how much you value $1,000. So let's compare our part C, part A, right? Let's determine how much more you have to pay if it's compounded daily versus if it's compounded yearly. Well, if it's 10 years, right, all you're really doing is taking, let's see, the compound interest one is more money. So it's 46,466 minus the other one, 46,152. And again, I've already ran these calculations ahead of time. I believe you get $314. Hey, that's like pie. And then 20 years, we're going to subtract this 67,471, and we're going to subtract 66,564. And the difference I get here is about $907. Now, look, that's not a lot. Now, I mean, it is a lot. I mean, $907 is like almost 2 PlayStation 5s, which I would enjoy having. But if you compare that to $67,000, I don't think the 900 is your main concern, right? If you're that deep in debt, I don't think the extra 900 is that big of a deal. But maybe you do care about that. And so maybe the model you use, it depends. And now we're going to use one more model. Let's use the continuously compounded interest formula. And this is A equals P to the RT. And we're going to do the same calculation. And then it also says, is this closer when the interest is compounded yearly versus daily? So I'll write the general real quick, right? Your general, you see this is 32,000. E to the rate is 0.0373 T. Okay? That's your general. So let's find A of 10. You see that's 32,000 times E to the 0.0373 times 10. That's exactly what that is. I've already run that calculation. I sound like a nerd when I say that, right? Yeah, I've already run that calculation, actually. And so there's that. And then A of 20 equals about 67,474. Okay? And there it is. And now you ask yourself, is this closer? I'm going to highlight this blue. Is this closer to when the interest is compounded yearly or daily? Now, look, the difference isn't super significant. It's sizable, but not super significant, right? But if you compare it, right, let's take, for instance, A of 20, right? For 20 years, continuously is 67,000 versus this 67,000. Oh, my gosh. That only differs by $3, right? That's a very minimal difference, whereas it's roughly still $900 between this one and this one. Similarly, this amount's only off by $1, one single U.S. dollar, one George Washington, right? Whereas this and this are still roughly $300 apart. So what is it closer to? I say closer to the daily, or I'll say compounded daily, yeah? Closer to the compounded daily model. Okay? That's what it's closer to that. And you might, if you'd like, underline this and underline that, so you can see the similarities here. Okay? And that's it. It was just a comparison here. And this makes sense because earlier we said that the continuously compounded interest formula is just when you increase into infinity. And the thing about the daily rate is we did 365, which as a fraction, 1 over 365 is really, really, really small, right? And so that's why this is so close. It's because we've picked a big number for n. It's by no means close to infinity, of course, but, it's big. Okay. Last piece of this question, we want to say, okay, we graduate college at 22 years old. After some time has passed, you haven't paid off any loans. Shame on you. You should pay those off. Look, not shame on you if you can't afford it. Of course, it's not on you. I just meant sad story for you because that means you're going to end up owing more, and I feel sorry because that's not a situation I want for anybody. And so you haven't paid off your loans. You currently owe $43,000. We ask, how old are you now? Okay? So, and we're still using the continuous model of growth for this. So we'll use our particular equation. I know that my final amount is $43,000. Whoa. Oop. Which equals my initial amount, 32,000, times e to the 0.373 t. Now, see, the thing is, we don't know what t is, right? So we got to find t. So we're going to solve this using logarithms. I'm going to first isolate my exponential. I'll divide both sides by 32,000. So I'll say this is 43,000 over 32,000, which, by the way, that's just 43 over 32 because you can cancel those thousands, right? Equals e to the 0.373 t. And if you take this, well, actually, I guess you don't even have to take the log of both sides, although I might. Let's say, I don't know. I don't care how you do it. You can convert to log from here because we have base e isolated, or you can take the log of both sides. Let's just convert, right? I'll draw this in blue. Convert to log. The base is log base e, so we're going to use natural log of the argument, which is 43 over 32, equals the exponent 0.3. Whoa. 0. Whoa, careful. Holy, oh my gosh. Almost made a fatal mistake there. We say, whoa, 0.03. Heavens, be careful. Okay, so it is blue. Sorry, just making my edits. 0.373 t. So what does that tell me, right? What is t? Well, I'm going to move this up here. I'm going to say, well, I divide by that decimal value. T is natural log of 43 over 32 divided by 0.0373. There you go. Now, see how this is super accurate. You have found the time accurately without rounding. Now that you found this expression, you can calculate this, okay? Calculate this, and then you can round that, okay? So what we've got here is natural log of 43 over 32, and this is being divided by 0.0373 equals 7.92. I'm just going to round to 2 decimal places. This is roughly 7.92. By the way, you see how I use that symbol? That means approximately, not exactly. Equals is exactly. So this is 7.92 years, which if you want to round, it's about 8 years, right? If you want to round to the nearest whole year. So you will be 22 plus 8 is 30 years old. That's how old you'll be. Okay? So in the next, after 8 years have passed, you'll owe $11,000 more. And I'll tell you something, guys. Those 8 years pass quicker than you might think. You might say, Mr. Spake, how would you know? You're 25. Only 3 years have passed. And I say, I still get it, though. Still, time is passing very quickly now that I've graduated college. All right. And there it is. Now, I'll tell you this. The test probably ain't going to be that easy. You might say, what, easy? Mr. Spake, that wasn't easy. I said, well, I'll tell you this. All you did was plug stuff in, right? You plugged in initial values, you plugged in a rate, and you used that calculator to make a prediction. The only not easy part was this last one. But this lesson, the difficulty doesn't lie in the calculations. It lies in the concepts, the understanding. Are you understanding the differences between these different models and the similarities, right? Notice every single model got us a ballpark same answer, but they have tiny differences. Okay, let's move to the next one. Number 2, and I really like this one. So we say, when rabbits were first brought to Australia, they had no natural enemies, which I find hard to believe, but hey, if they didn't have natural enemies, they didn't have natural enemies. I guess the snakes were full. So their numbers increased rapidly. Let's assume that there were 60,000 rabbits in the year 1865, and that 2 years later, in 1867, that number increased to 2,400,000, which is a heck of a lot of bunnies. We're going to assume that these increased exponentially with the number of years that elapsed since that time, like 1865. So this one, part A, tells us to use the model for exponential growth. It's outright flat gives it to us, and it wants us to find the particular equation. Now, here's the thing. You know, based off the information given, you know the starting amount of rabbits, you know the ending amount of rabbits, and you know the time is 2 years passing. What you don't know is the rate. What's the annual rate of growth of these rabbits? And that's what we seek to find. Okay? So let's plug some of this stuff in. I say that I keep wanting to say 24 million. 2,400,000 equals 60,000 times 1 plus r to the t is 2 years. Okay? And if you want to write that out to the side, you can, right? A equals this, P equals that, blah, blah, blah. I'm not going to bother doing that here. Now, we need to solve for r, right? Whoa, what's happening? Okay, so I'll divide both sides by 60,000. And I'll put this to the side. 2,400,000 divided by 6,0,0,0,0. That is, I've run the calculation on this problem multiple times. I know that this is 40, okay? That comes out to exactly 40, which equals 1 plus r squared. Now, how do I find r? Well, that's like a quadratic, ain't it? That's 1 plus r squared. That's a quadratic equation. It says it's already a perfect square. We know that we can take the square root of both sides. Right? I can take the square root of both sides. If you want, I'll write it like that. Okay, square root of 40 equals square root of 1 plus r squared. So this just gets, and don't forget, you should do the plus or minus 40. I'll tell you, though, it's not going to be negative root 40 because the rate is exponential growth, so it's positive. But I'll keep it for now. Plus or minus root 40 equals 1 plus r, right? Therefore, that tells me r equals negative 1, and you could say plus or minus root 40. But it's not negative, right? So I'm going to say not negative because growth. So we will just X that out. Okay? And that's our answer. R is negative 1 plus this. So our equation, we're going to get, what's our particular? I'll say the particular equation. I'm going to do this in blue so that there's not too much red overlapping, okay? The particular equation is A equals 60,000 times, now it says 1 plus r. 1 plus r. Well, that's just 1 plus negative 1 plus root 40. And so we don't really need those parentheses. 1 plus negative 1 cancels. So all this is inside is root 40. So this is the square root of 40. And then this is raised to the power of time, t. Okay? And if you want, you could express that as 2 root 10 as well. I don't know. What do you think? Should we do that? Should we do 2 root 10 or should we leave it as root 40? I suppose I've told you we always want to simplify, so I guess we can write either. I'll say or A equals 60,000, and then I'll say 2 root 10 to the t. Personally, I'm more inclined to use square root 40 so that the base is just very simplistic, right? Like you get rid of the square root, fine, it's easy. But whatever, okay? It's not a big deal here. Okay. So let's see, how many rabbits would we predict in 1870? Well, that's a final amount is 60,000 times, let's say this is square root 40. You can use 2 root 10. Those are literally the same thing, okay? I don't care. Square root 40 is less to type into a calculator. To the power of t. Now, 1870 is 5 years after, right? You say 1865 to 1870. That's 5 years, right? So, this is to the power of 5. And we will round. Yeah, we'll round to the nearest whole rabbit. So we will go ahead and do this calculation. We'll say 60,000 times square root 40 to the power... Oh, whoa. Careful, Mr. Spake. Careful. Where's my power? There's my power to the 5. Yeah, well, huh? That's a lot of rabbits. And it's also different from what I got. Oh, because I did a decimal approximation, huh? Yeah. Sorry, I'm looking at my notes I took, and I did a decimal approximation of 6.326 to the power of 5, which gets us... look at that, guys. Look at that. Do you see it? When I use square root 40, which is the ultimate accurate answer, I get this precise number of rabbits. But when I use a rounded decimal up to 3 place values, which honestly, a lot of times we like up to 3 decimal places, that's a difference of, let me see here. Is that like 700,000 rabbits? That's a pretty significant amount, I'd say. So looks like it's better to not round. So 607, 157, 310. I feel like I'm memorizing a phone number. I say 607, 157, 310. Is it 310 or 11? I round up. 11. I say rabbits. Okay? This is using the exact model. If you choose to round, it's okay, but you might want to use a lot of decimals, because if you round too little, you do a significant rounding job, your answer is going to differ by hundreds of thousands of rabbits, which maybe, considering there's 600 million of them, isn't a huge thing, but it's still a lot of bunnies. All right. Let's figure out now, according to your model, when was the first pair of rabbits introduced to Australia? And when you say first pair, of course, you're implying 2 bunnies. We don't get many bunnies from one bunny, sadly. I don't think rabbits are capable of mitosis, at least not on a cellular level, yes, but not like a body level. Whatever. I don't know biology terms. So let's see. So the final amount should be 2 rabbits, right? And we're going to compare this to 60,000 times my square root 40 to the power of t. So, okay, let's solve for t. We'll divide both sides by 60,000. This is 2 over 60,000, which actually, isn't that 1 over 30,000? Okay, which equals square root 40 to the t. Now, what are you going to do? Are you going to convert to log? I suppose you can, right? If you want to, or you can take the natural log. I don't really care in this case, because it doesn't really give us any guidance or context. So let's just convert to log. Okay, I'll say whoop, whoop, whoop. I'll say convert to log. The base is 40, so we will say log base square root 40 of the argument, which is 1 over 30,000, equals t, which is our time. Okay? Yeah, I like it. Let's do that. Let's go to our calculator, click math, go down to log base. We're going to do square root 40 in the bottom, and we're going to do 1 divided by 30,000 bunnies. Negative 5.589. Let's say negative 5.59. That's roughly negative 5.59 years. You say, well, net time can't be negative, Mr. Spake. I say, well, it can if you're on a timeline, right? If I say this is, I'm going to call that roughly 6 years, then this is about, let's see, 1865 minus 6 years puts us in 1859. We would guess that these rabbits were first introduced in the year 1859 because it's 6 years back from our initial data point from 1865. So you kind of reverse predicted, right? You've reverse engineered, making a prediction of when they first came. Okay, moving on. Let's use the law of exponential change to answer the following. Let's write the particular equation for this function. So similar stuff, yeah? You've got y equals c e to the kt. And this is where you know some information. You know that the final amount was 2,400,000 equals the beginning constant amount was 60,000. E to the k times t was 2. Now look, you'll divide by 60,000. You'll get 40 on the other side equals e to the 2k. And if you like, convert again, right? Let's just convert to log. Or you can take the natural log of both sides. Let me demonstrate that again, okay? I'm just going to demonstrate that again. I'll take natural log of 40 equals natural log of e to the 2k, which means natural log of 40 equals 2k natural log of e, but that's just 1. So natural log of 40 equals 2k, therefore k equals 1/2 times natural log 40. You say, where the heck did he get 1/2? I divided by 2, silly. I said natural log 40 over 2, but I wrote that as 1/2 times natural log 40 because I didn't want to make it a giant fraction. Okay? And that's k. You found k. So if you want to be ultra accurate, right, the particular equation is y equals 32,000. No, that's the lone one. Sorry. What do we start? 60,000 rabbits times e to the k, which is 1/2 natural log 40 times t. That's your particular equation. I don't want you rounding that, all right? Do not round 1/2 natural log 40. Ooh. You say, why, Mr. Spake? Why? For accurate predictions. I want to make accurate predictions. Okay. Now let's make the same prediction here, okay? And we're going to compare this one. So we just say y equals 60,000 e to the 1/2 natural log 40 times t, which is, let's see, it was 5 years, right? And so we will say that this is roughly, we're going to round to the nearest whole rabbit. We're going to do 60,000 times e, so we do second e to the x we said it's 1/2, so that's 0.5 natural log 40 times 5. And look at that, 607,15731. Wait. Oh, shoot. Not 6,000, Mr. Spake. 60,000. Okay. I was wondering why something was up. If you notice, see this value that I'm highlighting versus this value versus this, they are almost exactly the same, aren't they? I feel like they should be the same. I don't know. So something about this calculator might be different. But anyway, we do get the same number if you round to the nearest whole. 607, 157, 300 rabbits. Oh my gosh, it's the same. Okay, I'm going to box this one up here. I'm going to just make it clear to you guys while you're taking the notes. Box this one here. And then we box this one. And say, it is the same prediction. So I'm just using this to call your attention to, at the beginning of the video, I said that all of these things were basically telling the same story, right? And so in one instance, we used just the general exponential growth function. In the other, we used the law of exponential change. And our functions look different. Look, this versus this, they look different, but they still make about the same prediction. Yeah? Now, going on to this next part, we say, prove algebraically that the value of 1 plus r equals e to the k. Well, we know that 1 plus r is square root 40. Look, it's all the way up here, right? 1 plus r, where r is this, right? This is that whole thing. I said 1 plus negative 1 plus root 40. Those cancel, so it's just root 40, yeah? So we're going to prove that these are the same thing. 1 plus r equals the square root of 40. Now, e to the k equals, well, what was e? The k was, it's e to the 1/2 natural log 40. So this is what we seek to, we want to show, right? We'll say show that square root 40, which is 1 plus r, is equivalent to e to the 1/2 natural log of 40. Well, there's perhaps some variety of ways you could do this. Why don't we just take the natural log of both sides? Let's just do that. Natural log of square root 40 equals natural log of e to the 1/2 natural log 40, right? If you like this, there's multiple approaches. You can do this another way, okay? And honestly, if you're really good at this stuff and you're a true mathematician, you already understand that these things are equal because it's obvious. But it may not be obvious from the student perspective. That's why we're doing this, okay? So I take the natural log of both sides. Let's use the power rule. You say natural log of 40 equals 1/2 natural log 40 times natural log of e. But of course, we know that natural log of e is just 1. So this says natural log of root 40 equals 1/2 natural log 40, right? Well, isn't 1/2 natural, aren't those the same thing, right? Yeah, right? Because look, natural log of square root 40, that's 40 to the 1/2, which is true via the power rule. And there you go. The values are equal. So essentially what you can say is if you work backwards, you can go from here to here and then make the conclusion that they're equal. So I say, therefore, the values of 1 plus r, that value, equals e to the k. And if you're not sure why we did this, I want you to call your attention. Look. A, y. Both of those mean final amount. 60,000, both those mean initial amount. The power being t and t, both of those are the same. So what's the base? The base here is square root 40. The base here is e to this power, and then to the power of t. Okay? And so therefore they are equal. Now, what do these things tell us, right? What do they tell us? Well, Well, we said that r equals, it was -1 plus square root 40, which now let's approximate that as a decimal because we want to make sense of r. What is r telling us? So -1 plus root 40, we're going to do -1 plus square root of 40 is 5.324. 5.234. Which means, right, that's a decimal. That means it's a percentage. So that's a 523% increase. But what kind of increase? Annual. It's a 523% annual increase of the rabbit population. What does K tell us? Well, K is 1/2 natural log 40, which that's approximately, let's do 1/2 that, right? 1/2 natural log 40. About 1.84. That's roughly 1.844. That tells us this is 184%. Well, it's not an annual increase, right? Because what kind of function is this? If we look at, right, it's the law of exponential change, this one, which looks, right, this guy looks exactly like continuously compounded interest. So, K isn't the annual increase of the rabbits. It's 184%. You can say instantaneously or continuously increasing. Continuously, or I should say continuous increase. Okay? And that's the difference. So what does this mean? Why, right? And which model might we prefer to model this population growth, right? Well, if you're analyzing the rabbits on a yearly basis, saying every year this is what our rabbits are going to be, well, you would use the first one, right? We'd say, hey, the rabbits every year looks like they're growing by about 523% of what their population was the previous year. The continuous rate, right? It's a rate of continuous change, means every second, right? And I say every second, but really I mean no seconds, really. I mean just instant, 184% increase in their population, right? Between what their population was, right? It's a continuous increase. What would we do with that continuous increase rate? I don't know. I think the annual one we might be more interested in, and more often than not, that's why you're going to see this particular equation be used for this type of problem. But again, what we're doing is we're exploring the ways different kinds of models essentially make the same predictions, but tell us different information about the problem. Okay? All right. Yeah. Okay? Yeah, sorry. I was just thinking. Okay. We've still got 2 more problems. I'm going to end the video here and pick up as and make it a part 2. Okay? I'm gonna just stop it here and start making part 2 because I don't even know how long this is. It's probably really, really long. I'm sorry. I don't even know if we'll have class time for all this, honestly. Okay, have a good night or continue to the next video. I will see you there. Okay?